Hello, I'm Mark Warner, founder of Warner Advisors, a consulting firm formed to assist clients in taking their advanced biotechnology from concept to commercial operation. The topic of this presentation is advanced downstream recovery, converting fermentation broth into products. While fermentation is often the focus on advanced biotechnology scale-up, downstream recovery is often the most costly and complicated portion of the overall process and worth exploring further. The first important concept to consider in commercializing a new biotechnology is that there is no substitute for a fully integrated process. Much of the presentation will focus on downstream recovery, but please keep in mind that it will need to be integrated with fermentation to have a successful scale-up. Many companies use modeling to do early stage planning and economic projections, and they're great for down selecting options, but when it comes to actual scale-up, modeling is not a substitute for pilot testing. The other thing to remember is while you can buy most downstream equipment as a package, centrifuges, filtration system, dryers, they need to be integrated as a complete system when scaling up. When operating a recovery system, tracking and operating or optimizing overall yield is critical. Making products by fermentation is expensive, and the ability to recover as much as possible is critical to reaching economic viability. As you run your pilot and demo plant, it's important to make sure you learn from all failures. I've seen cases where analyzing runs that have failed provides useful information to scale up, so don't be in a rush to discard failed pilot runs as useless without reviewing the data first. You're going to plug filters, you're going to have problems with your dryer. Use it as a learning experience. Looking at why scale-up of biotechnology is so difficult, there are a few key concepts to consider. The most important one is to understand that you have to start with the concept of what a commercial facility will look like and pull data from the pilot, not just try to replicate what the pilot system is doing. Feedstock is also very important. The type of feedstock and purity level has a direct impact on recovery strategy. Using representative feedstock early in the process is critical, along with understanding that everything that goes into the fermenter, media, antifoam, impurities in the sugar, all will become contaminants in the fermentation broth that will need to be dealt with. Finally, you need to understand what success looks like before you begin scale up. The most important consideration is what the product specifications are that are going to need to be met so you can develop them during your process. It's the equivalent of knowing the destination before you start a trip. If you don't know where you're headed, finding your final destination will be difficult. Advanced biotechnology was born out of advances in fermentation and synthetic biology, often making fermentation the technical focus of most companies. However, the overall process as it's developed to make a product, recovery will be as important as fermentation and can often be more complicated and costly. In developing a technical approach to recovery, the products out of the fermentation broth, there are two major pathways: products that are secreted into the broth and ones that remain in the cell wall after fermentation. Both of these systems will use similar operations, but they're often configured quite differently. As you start to develop a recovery process, overall yield and product quality will be a primary focus. These need to be optimized to end up with a process that is commercially viable. As noted on the previous slide, there are two major pathways to purification, depending on whether the product is secreted or remains inside the cell. These are shown on the following block flow, with the difference being the addition of cell disruption unit operation that is required for intercellular products. The table below shows typical unit operations used in advanced biotechnology. The remainder of this presentation will do a deeper dive into the strategic considerations in determining which technology works best for a specific process. The most universal operation used in downstream recovery is concentration and separation by centrifuge. It's important to understand the types of centrifuges and how they scale, as they are usually more complicated and less flexible than first thought. The primary types are distack, decanter, and high G tubular. The size of cells being separated is a key factor in determining the appropriate equipment. For most advanced biotechnology operations, the cells are usually in the zero 0.5 to 5 micron range, and typical fermentation broths are around 2 to 10% dry cell weight by concentration. The chart at the bottom gives a visual representation of the typical operating ranges and centrifuges discussed. You can see if we overlay the area that represents typical concentration and cell size within advanced biotechnology, this shows that disc stacks and tubular centrifuges are the two most likely to have application, although as I will discuss later, the tubular centrifuges are not really scalable for commercial operations. Let's look at some lessons learned on centrifuges. As I mentioned a minute ago, particle size, G-force, and total solids are key criteria in determining the right centrifuge. I often see pilot plants using the high G centrifuges, and while they provide a good separation, they're not scalable and don't have a commercial equivalent. This really makes using them during scale-up a mistake many times. Decanters are desirable as they have higher throughputs and lower capital costs than disc stack centrifuges, but they're not often a good fit for advanced biotechnology. There are exceptions, but they are not usually worth a significant development effort. Disc stack centrifuges are the most widely used. However, there are many ways to configure them. When sized correctly for flow and solids handling, they can operate continuously for years. By contrast, when the wrong configuration is selected, they can often produce significant mechanical and quality issues. Moving on to cell disruption, I'm going to provide a simplistic example of options and implications for the overall process. In lieu of cells, let's consider a visually easier example of pistachios. Like our cells, there's something inside we want, the nut. And there's different ways to disrupt the shell to get to the nut. How we disrupt the shell will impact the recovery and quality of the nut we get. In the case of secretion, the nut and shell are both intact. Bead milling is a process that cracks the outer shell, releasing the internal material. Enzymatic hydrolysis is similar to bead milling, but done chemically, not mechanically. Acids and solvents can be used to disrupt the cell, but are often a little more aggressive. Finally, homogenization is the most aggressive cell disruption technology and completely deconstructs the cell. The important part of this slide is the more you deconstruct the cell, it will give you more access to the product you're looking for, but it also creates a matrix that can make it quite difficult to extract your product. There's a broad range of disruption technologies that can be used, and determining which is the best fit will depend on your overall process. Organisms that secrete product into the broth do simplify the process, but they often have lower yields. As mentioned on the previous slide, the higher level of deconstruction is done, the more complicated the recovery becomes. A secondary item to consider that is often overlooked is that any residual biomass will be impacted. Most biotechnology processes generate some type of spent biomass. The more this is deconstructed, the less value that biomass will have. Extraction and purification has the widest range of technology options in downstream recovery. It's not usually a question of whether the product can be recovered, but whether it can be done in an economic manner. It's important to consider that fermentation is not always a static operation. If changes are being made in the front-end development of your process and fermentation, that will impact your downstream recovery efforts. Filtration systems have made significant advances in recent years and can often be a cost-effective, especially more than previous versions. That said, it's important to understand that things like filter life and how these filters can be cleaned and reutilized have major cost implications and need to be understood. And finally, don't be too quick to discard legacy technologies like solvent extraction or distillation. They can often be the most robust and cost-effective solution. This table is extracted from a white paper I published regarding strategic approach to process scale-up. It shows a range of recovery technologies and the likelihood they will be viable for various processes. This determination is primarily cost-based, with higher value products having more options for purification than items like fuels and chemicals. As recovery processes are developed, wastewater is often a major factor that is overlooked and can create a problem during scale-up. Fermentation processes generate significant wastewater, and downstream recovery has the potential to add to it. Optimization is critical, as wastewater can have a significant capital and operating cost impact. It's common for wastewater treatment to add, say, 10-15% to the overall capital cost of a project. As the process is developed, it's critical to get representative samples from the pilot operation and analyze them for key criteria. This will be valuable for permitting and facility design. Evaporation and drying is usually the highest energy used in downstream recovery and a significant capital cost. The best option will usually depend on whether the material you're trying to dry is water-like or a semi-solid material. When looking at various drying technologies, it's best to compare them on a water evaporation rate basis. This will allow you to make a fair comparison. Evaporation alone is usually more energy efficient than an overall drying process and is often utilized in a two-step drying process with evaporation followed by drying. Also, direct-fired systems are often much more efficient than indirect heated systems with things like steam. When considering drying options, it's very important to understand what energy sources your ultimate commercial process may have, say natural gas or high-pressure steam. The type of energy source available will often constrict the type of dryer you can use. It's important to understand product specifications early in the process, as many materials with a moisture concentration of less than 10% will appear dry, but specifications may require a lower moisture level, and this can often be difficult to achieve. The last few percent of dryness can be as hard to achieve as the entire remainder of the drying process. Skin temperature, basically the temperature of any hot surface during drying, can impact color and quality of your product and should be considered. On food products, direct fired systems can impact things like flavor and need to be considered. Solids handling of the dried material can be difficult and needs to be considered during scale-up. Many advanced biotechnology processes end up failing because of their inability to do the dry material handling. Finally, I see freeze drying used a lot during pilot operations to generate samples, and while it does meet this need, it is usually not scalable and can produce samples that are sent to clients that can't be reproduced at commercial scale. Looking at some common pitfalls for the overall downstream development process, let's do a summary of the presentation. Using high-G centrifuges and freeze dryers are not often scalable, and when used at pilot scale can cause long-term problems. On cell disruption, while homogenization is often used in pharmaceutical processes, it's not typically economically viable for commodity products. Similarly, TFF and chromatography have been used and can sometimes be economically viable, but still there's many times where they just don't have the economics that make it work. Keep a focus on wastewater throughout the process. It can have significant capital and operating cost implications and needs to be considered throughout the process. A brief background on myself. I'm a chemical engineer with 30 years in advanced biotechnology and chemicals, focused recently on taking first-of-a-kind technologies to commercial scale. I'm currently an independent consultant supporting many companies in advanced biotechnology. Before consulting, I worked for industry leaders including Impossible Foods, Solazyme, and Harris Group. I've had the opportunity over the years to commercialize a broad range of technologies, basically including sugar-based aseptic fermentation, syngas methane, and a broad range of downstream recovery technologies. I've published a series of articles on similar subjects that may be of interest to those listening. They include a white paper on scale-up through contract manufacturing, a white paper that includes a test to evaluate commercial readiness, and a white paper on strategic approach to scale-up. All of these can be found at the web page shown below.